Suppose that e sub 0, e sub 1, e sub 2, and so on is a sequence defined as follows. E sub 0 equals 12, e sub 1 equals 29, e sub k equals 5 times e sub k minus 1 minus 6 times e sub k minus 2 for each integer k greater than or equal to 2. Prove that e sub n equals 5 times 3 to the n plus 7 times 2 to the n for every integer n greater than or equal to 0. So first we have to identify our predicate p of n. Remember, we can't include the universal quantifier in the predicate. So let's first talk about why we need to use strong mathematical induction instead of just normal mathematical induction. In this case, we are going to be utilizing this recurrence relation. And if you notice that this recurrence relation tells us that each term is determined by the previous two terms, e sub k minus 1 and e sub k minus 2. If we want to use this in mathematical induction, then most likely we're going to need to not only prove two base cases, but also we're going to need strong mathematical induction rather than just normal mathematical induction. So let's talk about why we need to use strong mathematical induction here. We will be utilizing this recurrence relation throughout the inductive step, and this recurrence relation says that each term, e sub k, is determined by the previous two terms, along with some math to combine these two things together. So because each term is determined by the previous two terms, we will need to use strong mathematical induction rather than normal mathematical induction. Now, if we're using strong mathematical induction, we have to consider how many base cases we need to solve. To determine the number of base cases that we need to first determine the gap between the largest index in the recurrence relation, which in this case is k, and the smallest index in the recurrence relation, which is k minus 2. The gap between these two numbers is the number of base cases that we'll need to be able to solve this strong mathematical induction proof in order for our proof to be valid. So when we're proving that the predicate p of n is true for every integer n greater than or equal to 0, then that means we're going to start with n equals 0, but we're also going to show that the statement is true for n equals 1 in this base case. So really there are two base cases. Let's start with p of 0. P of 0 is what I get when I plug in 0 into this entire equation. Keep in mind that p of n is not just this right-hand side here. P of n is the entire equation itself. And so p of 0 would say specifically that e sub 0 equals 5 times 3 to the 0 plus 7 times 2 to the 0. Now, I'm going to put a question mark here because this is the thing that we want to show. We want to show that this is true. So I put a question mark there to avoid asserting any truth value. A question cannot be true or false by the definition of a statement. So let's show that this is true. Why is this true? Well, it's because on one hand, e sub 0 equals 12. That's given to us. So that's what the left-hand side represents. The left-hand side is just 12. The right-hand side here is 5 times 3 to the 0 plus 7 times 2 to the 0, which is just 5 plus 7, which equals 12. And this means that these two things, and so this means that e sub 0 equals 5 times 3 to the 0 plus 7 times 2 to the 0 because they both equal 12. So I'll put a check mark to show that we've verified that p of 0 is true. Now let's move on to p of 1, which says that e sub 1 equals 5 times 3 to the 1 plus 7 times 2 to the 1. Again, I'll put a question mark here to avoid asserting the truth of the thing that we want to show. We don't want to assume the conclusion, otherwise we would be using circular reasoning to lead to a tautology. But rather, I want to show that the left-hand side equals the right-hand side, and so therefore they must be equal to each other. Now, on the left-hand side, we have e sub 1. E sub 1 is given to us, which is 29. So the left-hand side is equal to 29. The right-hand side, we can compute. This is 5 times 3, which is 15, plus 7 times 2, which is 14, and that equals 29. And so the left-hand side and the right-hand side equal the same number, and so they must be equal to each other, which shows that the base cases are true. Now let's move on to the inductive step. I always start the inductive step the same way, by instantiating the letter k. So let's start by saying let k be an arbitrary fixed integer such that, now if you remember from the last video, k in strong mathematical induction has to be at least as large as the last base case, which in this case is 1. So we want to ensure that k is greater than or equal to 1, which is different than normal mathematical induction. Normal mathematical induction, we just start with the lowest number. But in strong mathematical induction, you start from the last base case. And this is the hard part of strong mathematical induction. We're going to assume that P of I is true for all 0 less than or equal to I less than or equal to k. That means we're going to assume P of 0, P of 1, maybe P of 2, maybe P of 3, maybe P of 4, all the way up to P of k, whatever k is. Keep in mind, k is fixed in the inductive step. We don't know what it is, and it is the arbitrariness of the letter k that can allow us to generalize this proof universally across the entire domain of discourse. So the best way to understand the inductive step is to first understand these two words, arbitrary and fixed. The reason k is arbitrary is so that we can generalize this inductive step universally across the entire domain of discourse. And the reason it's fixed is so that we can make precise claims about k and what we do with k. So keep in mind that k is a constant, not a variable in the sense that it varies. K does not vary. Whereas the letter n we can consider as a universally quantified variable in the sense that we can imagine n as being one number and then another number and then another number, and then the predicate P of n is true for all n greater than or equal to 0. So it's super important to understand the difference between k and n in the inductive step. We're assuming that P of I is true for all 0 less than or equal to I less than or equal to k. Let's figure out what that means. Well, we can take our predicate P of n and replace n with I. So I is sort of an index variable. I is going to tell us which of the values of P of n are true in our assumption for the inductive step. So I could be 0, I could be 1, I could be 2, I could be 3, all the way up to k, whatever k is. We don't know what k is, but we're not assuming that P of k plus 1 is true. We're assuming P of k is true, and we're assuming P of k minus 1 is true, and so on, all the way down to P of 1 and P of 0. We're assuming that all of those statements are true. Keep in mind that the distinction between strong mathematical induction and normal mathematical induction is that in normal mathematical induction, we would just assume that E sub k equals 5 times 3 to the k plus 7 times 2 to the k. Now, k falls in this region here from 0 to k, inclusive of 0 and inclusive of k. And so we are assuming that P of k is true. We are assuming that this is true. Just like in normal mathematical induction, we assume that this is true. But we're also assuming other things as well. And we get to assume those things and still prove the statement P of n is true for all n greater than or equal to 0. So we're assuming that this is true, but we're also assuming that E sub k minus 1 equals 5 times 3 to the k minus 1 plus 7 times 2 to the k minus 1. And we're also assuming this statement is true for k minus 2 and k minus 3. And we're assuming this all the way down to I equals 1 and I equals 0. However, for this proof, because we're using a recurrence relation where each term is determined by the previous two terms, it turns out that we only need these two parts of the inductive hypothesis. So in normal mathematical induction, you need to use the inductive hypothesis to prove that P of k plus 1 is true. Whereas in strong mathematical induction, you get to use P of k and P of k minus 1 and P of k minus 2 and so forth. but you don't have to use all of them. You have to use at least one of them to prove that P of k plus 1 is true, but you don't have to use all of your tools at your disposal to solve that P of k plus 1 is true. So to demonstrate that, we're going to use only these two pieces of the inductive hypothesis to prove that P of k plus 1 is true. What is P of k plus 1? P of k plus 1 is the statement that E sub k plus 1 equals 5 times 3 to the power of k plus 1 plus 7 times 2 to the power of k plus 1. Now I'm going to put a question mark next to this P of k plus 1 because I don't want to assert that this is true. I don't want to start with this in my proof because this is the thing that I want to end with, not start with. The way we're going to show that P of k plus 1 is true is we're going to start with just the left-hand side, and then we're going to take that left-hand side and do stuff to it, and we'll just keep doing stuff to it until we get the right-hand side, and then we'll be able to show that the left-hand side is actually equal to the right-hand side. So let's start with the left-hand side here, E sub k plus 1. Now keep in mind that k is greater than or equal to 1 in the assumption, and that means that k plus 1 is greater than or equal to 2. And the reason why that's important is because we are about to use the recurrence relation. This recurrence relation can only be used when the index itself is at least 2. But since k is greater than or equal to 1, that means k plus 1 is greater than or equal to 2, which means that we can use this recurrence relation on E sub k plus 1. To do that, though, we have to shift this index from k to k plus 1, which means we need to also shift this index from k minus 1 to k, and we need to shift this index from k minus 2 to k minus 1. So let me show you how to apply this recurrence relation to E sub k plus 1. This would give us E sub k plus 1 equals 5 times E sub k minus 6 times E sub k minus 1. And this is true by the recursive definition of the sequence. Now we can do stuff with E sub k and E sub k minus 1 because in our inductive hypothesis, we know things about E sub k and E sub k minus 1 specifically. Again, k is fixed, which means k minus 1. And remember that k is a fixed integer, which means k minus 1 is also a fixed integer. So now I'm going to substitute from the inductive hypothesis these expressions into the result of the recurrence definition. Now, when I do this substitution, I always substitute with parentheses, just because we might need to use the distributive property, which we will in this case. But now we've taken E sub k plus 1 and we've turned it into something else. And this new thing is a little bit closer to the right-hand side of P of k plus 1. So we've taken the left-hand side, we've done stuff using the inductive hypothesis, and now we have something that's a little closer to the right-hand side of P of k plus 1. Now, it's really important that whenever you use the inductive hypothesis, any part of the inductive hypothesis, you have to clearly tell the reader that that's what you just did. So I'm going to say by the inductive hypothesis. Every proof by mathematical induction must include this justification at least once. This justification being by the inductive hypothesis. You have to use the inductive hypothesis in mathematical induction, or else it's just not mathematical induction. So next, I'm going to simplify by distributing this 5 and distributing this minus 6 here, which is 25 times 3 to the k plus 35 times 2 to the k, and then minus 30 times 3 to the k minus 1, minus 42 times 2 to the k minus 1. Now, I would like to combine like terms here, but unfortunately we can't quite combine like terms in the way that this is written because here we have a 3 to the k and here we have a 3 to the k minus 1. Now, if these were both either a 3 to the k minus 1 or a 3 to the k, that would be super convenient. So what I'm going to do here is a little bit of a trick. I'm going to factor out a 3 from this 3 to the k, and I'm also going to factor out a 2 from this 2 to the k. So if I pull out a factor of 3, this would be 25 times 3, which is 75. But that's the result after I pull out a factor of k from the 3 to the k. So we would only have 3 to the k minus 1 left over. And I'm going to do the same thing with a factor of 2 here. This will be plus 70 times 2 to the k minus 1. And then we're going to leave everything else the same so that we can prepare to combine like terms. Now let's combine our 3 to the k minus 1s. If I have 75 of them and then I take away 30, then I would only have 45 3 to the k minus 1s. And if I have 72 to the k minus 1s and I take away 42 of them, then I would only have 28 2 to the k minus 1s left over. Now let's just briefly recap what we've done so far. We started with e to the k plus 1 here. And then we did some stuff, used the inductive hypothesis, did some more stuff, did some more algebra, and now we're here. But let's remind ourselves where we're trying to go. We're trying to do stuff to this left-hand side to eventually get this right-hand side here. But if you notice, these are 3 to the k plus 1s here and 2 to the k plus 1s here. And currently, our answer is in terms of 3 to the k minus 1 and 2 to the k minus 1. So if we want to get the correct power, let's reabsorb some of those factors of 3 into the 3 to the k minus 1, and let's reabsorb some of the factors of 2 into the 2 to the k minus 1. Let me show you what I mean by that. We could take this number 45 and we can factor out a 3 squared, or a 9. So I can write this as 5 times 9, and then times 3 to the k minus 1. And then with this 28, I'm going to pull out two factors of 2, which is 7 times 4 times 2 to the k minus 1. And then I'm going to rewrite these factors as powers of 3 and powers of 2. So this equals 5 times 3 squared times 3 to the k minus 1, and then plus 7 times 2 squared times 2 to the k minus 1. And then we can use the law of exponents, which says that if you have the same base, we can simply add the exponents together. So this equals 5 times 3 to the k plus 1, and then plus 7 times 2 to the k plus 1. 2 plus k minus 1 is k plus 1. And this is the right-hand side of p of k plus 1. So let's recap again what happened. We started with e sub k plus 1, and we ended up with the right-hand side of p of k plus 1, which is exactly what we wanted to show here. This was a question initially, but now we've answered this question. This is a true statement because we took e sub k plus 1 here and did stuff to it, and we kept doing stuff and moving stuff around, and eventually we got the right-hand side. Now, I will say there are a lot of tricks here that a lot of students just would not be able to think about on a test. And this is why these questions are really tricky on tests, is because of these tricks. For example, in this proof, I thought about reabsorbing factors of 3 into 3 to the k minus 1. There was intention behind that because I wanted to turn this 3 to the k minus 1 into a 3 to the k plus 1 here. But I've been doing mathematical induction for a long time. And if this is the first time you've seen strong mathematical induction, then you might be a little confused by this trick that I pulled by factoring a 9 from a 45. That kind of seems out of nowhere. But there is intention behind it. And this is why when you're trying to learn mathematical induction, hindsight is your best friend. You want to be able to use hindsight to be able to predict how you would use mathematical induction for other problems. If you notice that the tricks that we're doing here are somewhat going to be similar to tricks that you might do on a test. But each mathematical induction proof usually has at least one trick that you just have to know about, or at least a trick that you, and that's why we do these videos, so that we can learn all of these tricks and so that we aren't surprised on a test. But I see a lot of students who think of this as sort of pulling a rabbit out of a hat. And that's the thing about magic tricks, is that you don't really understand a magic trick until you're explicitly told what the magic trick is and how it works. Oh, it's actually, there's a sleeve in the hat that where you pull it out and there's a rabbit there. That's kind of what we're doing here, is I'm trying to show you this is this is where the rabbit comes from, so that next time you see the rabbit being pulled out of the hat, it won't be as much of a surprise. So the end of mathematical induction is very ritualistic and very repetitive. Pretty much every mathematical induction ends the same way. This means that P of k plus 1 is true. And I always end mathematical induction by saying, by mathematical induction, P of n is true for all n greater than or equal to 0. And that's it. Thanks, everyone, and I will see you in the next video.